Zakharov Kuznetsov equation. Please, Felipe.
Okay, good afternoon. Thank you, Claudia, for the introduction and the invitation to be in this seminar. So today I would like to talk about this topic of maximal function estimate for solution of the linear Zakharov Kuznetsov equation, and then how to put in order to obtain local well-posedness for this equation, right? Okay, so that's the equation that we are looking at. So we have here we are going to have a real value function. Delta is the Laplacian. So we divide this as x is in the real line, and the y variable is in RT minus 1. Okay, and the time is in R. And then we have k is a positive integer. All right. So what I would like to do today, at least to comment on these three points, is talking about high dimensional Strichartz estimate, okay, for the unitary group associated to the Zakharov Kuznetsov equation, and then to deduce maximal estimate, which allows to prove local well-posedness for the generalized CK equation in the whole case whenever D is greater or equal than 4 and K is greater or equal than 4, complementing the recent result by Kinoshita and Herr and Kinoshita. So I saw Sebastian around there. To use some maximal estimate in order to prove pointwise convergence result for the flow of the generalized Zakharov Kuznetsov equation in any dimension, particular for the Zakharov Kuznetsov equation itself. All right. So the plan of the talk is as follows. So I'm going to give a long motivation. Then I'm going to tell you about what are the results and some remarks on that. So remarks will be all around. And then if I have time, I'm going to say something about the how to prove some of the results. Okay, so everything here is a joint work with João Pedro Ramos. So he's in ETH in Zurich. Okay, so we started with this. So we have the Zakharov Kuznetsov equation that went over there, right? And this is what derived by Zakharov Kuznetsov as a long wave small amplitude limit of the Euler-Poisson system in this framework of cold plasmas approximation. Okay, so that was a formal derivation, and then we did, I mean, David Lance, Jean-Claude Sot, and myself, we justified this long limit rigorously. Okay. Then, what other properties that we have about this CK equation is this is not a completely integrable system, right? However, it has a Hamiltonian structure and possesses at least 3 conserved invariants. So we have this, the first invariant here. Okay, so we have the mass is invariant, and this energy is invariant. Okay, and as we know, see, we can combine at least M and E in order to obtain a priori estimates and then extend local solutions globally if we have those results at hand, right? Okay, so I always say something about so you can say, well, the CK equation is just a generalization of KdV equation. And then you can say that if you are mathematically is correct, right? But from the point of view of physics, right? The KdV is describe the propagation of nonlinear wave in shallow water. Okay, so it's different from what Zakharov Kuznetsov model does. And then if you want to have a 2D generalization of the KDB equation, it should be Kp, right? Either the plus or minus here, and when you have a derivative -1, okay? So this is more appropriate from the physical point of view. This is just a generalization of KDB, but anyway, you can look at CKS generalization of that mathematically, right? Okay, so since there are young people attending the seminar, right? So I just want to tell you what is the notion of well-posedness that we use here, right? So we consider the initial value problem like this, right? And then we are going to follow Cato's definition of well-posedness that includes, as always, existence, uniqueness, and then he asked for persistence, okay? So what is the meaning of that? Well, if you started with the initial data in X in a functional space, we would like to have that the solution, the corresponding solution, describe a continuous curve in that space, all right? So this is the additional ingredient in the well-posedness notion of Cato. And then, as always, continuous dependence on the initial data, okay? And in addition to that, if this condition satisfied for a small time, so we say that the initial value problem is locally well posed. On the other hand, if we have that satisfied for any time, we say that the initial value problem is globally well posed. All right. And so this in general, we are going to deal with dispersive equation, and the natural space to work with then is the solar space. Okay, so it's, let me see if I can get out this guy here. Okay, so you can see the usual definition of the solar space in RD. Okay, so we keep going. And then, okay, so you have the initial value problem, and you would like to know in which space you can try to solve, right? So one motivation before was you have this integral, this invariant, like L2 invariant, H1 invariant, and then you try to prove local well-posedness in those spaces, and then try to extend it globally, right? But then you would like to see what is the largest space where you can obtain local well-posedness. So one criteria for do that is the scaling, right? So in particular, if you have an equation satisfying, in this case, that happens, right? So you have a solution of the equation with initial data NHS. And then you can see that this is also a solution with this initial data. And then you would like to know how many derivatives are invariant by this scale, right? So this is a folklore. Well, you can say, well, what happens if this is equal to 0, and then S is greater or equal than that number, so you make chance to have local well-posedness. Otherwise, the definition that we had before was continuous dependence may fail. All right. So this is the indices that we are interested in, right? So, but this is just a guess, right? And then sometimes there are many examples where we don't attain this value. All right. Okay, but this is the reference to keep in mind, right? And then try to solve the initial value problem. Okay, so next I'm going to tell you about what has been done for the Zakharov Kuznetsov equation, right? In 2D and 3D, and then with different powers and so on, okay? And so we can go to the first result. This was in 1995 by Andrei Faminsky, where he proved that this the initial value problem associated to the Zakharov Kuznetsov equation in 2D is locally well posed in a case for S greater than or equal to 1, when S is an integer. Okay, and the method is combined smoothing effects and contraction mapping principle. Then in 2009, with Ademir Pastor, we prove we can extend the result of Faminsky, inspired by the result of Kenny Ponce-Vega for KDE equation, right? And then we get a local well-posedness in HS with S greater than 3/4, okay? So if you check back what we have, right? Here, this is really far from that point, right? Okay, so you keep going, and then you find this result by Molinet and Pilot, at the same time with Axel Grunrock and Sebastian Herr in 2015. And so this is a major improvement of the previous result. They get a local result in HS is greater than 1/2. Okay, so on the result given before, right? So you can extend globally the solutions in H1 and above, right? Recently, Kinoshita in 2019 obtained the best possible result using contraction mapping principle, right? So he proved local well-posedness in HS for S greater than -1/4. Okay, so and the key, okay, so he used Burgen spaces, all that stuff, but the key element there, beside the beautiful analysis that he does, is this Loomis-Whitney inequality that concern with some convolutions in some manifolds, right? So Kinoshita get this result, the local result, and of course, the local result for any HS greater or equal than 0. All right, so now we move to K greater or equal than 2. So we have the scale is like this, is 1 minus 2 over K, right? And then you have some chart result obtained by Ribot and Ventus for K greater or equal than 4. So if in 2015, Axel Rock also obtained local well-posedness in the case K equal to 3 for all the scale, S greater than 1/3. And then in particular, when you have K equal to 2, what is called the modified Zakharov Kuznetsov, you got the result of Kinoshita, and he proved that the best possible result is HS S greater or equal than 4, okay, improving a little bit what Ribot and Bento did for S greater than 1/4. And then you can have a global result below H1, and it was obtained by Jarja, Farah, and Rudenko, and they prove this is global if S is greater than 3/4. Okay, so they use this the I method. So. All right, so we moved to 3 dimension, and then we found the result of K equal to 1, and so there was this result by Ribot and Bento, and they prove local well-posedness in HS greater than 1. So previously, Jan Clouseau and myself obtained a result, I don't know, probably 9/8 or so. And then Molinet and Pilot prove that the result of Ribot and Bento are global in S greater than 1. And then in 2020, Herr and Kinoshita established optimal local well-posedness using Picard iteration, right? For data in HS is greater than -1/2. And so global well-posedness is obtained for S greater or equal than 0, right? For K greater or equal than 3, they are resolved by Grunrock. So he obtained local well-posedness for S greater than the scale, 3/2 minus 2 over K. For the case K equal to 2, Grunrock and Kinoshita obtained similar result, right? And then this is S greater than 1/2. And then Kinoshita additionally showed that he can prove it in 1/2, right? And then globally too. All right, so in the case of the modified CK equation, I just want to tell you that So you obtain global result, but you have to be careful with the size of the initial data, right? So you can combine the mass and the energy, right? And use the Gallardo-Nirenberg inequality in order to obtain an a priori estimate for the first derivative of the solution, right? And so you can do that, right? And you can see that there appears something. This is a ground state solution of this elliptic problem that somehow this is hiding. Okay. And then what is said that this is, well, if the initial data, you start with initial data in H1 with L2 norm smaller than the ground states, so you can have a priori estimate for that, for the gradient of that equation, the solution of the equation. And so you can guarantee the existence of global solution for the problem. But then what happens is you are above that. Okay, so actually you can be more precise if you have the L2 norm, the L2 norm of this H1 data below this number, and so you can have global results. And so recently Farah, Holmes, Rudenko, and Jan, they show there are solution of the IVP associated to the 2D L2 critical equation that blow in finite or infinite time, and they implement the strategy of Ivan Martel and Frank Mer for the critical KDB equation. All right. All right. So, okay, this is next. No, previous. All right. So at this point, this is the advertisement point. Okay. So it's like in the soccer games. So we have an advertisement. And then I had to tell you that in the 3D case, if you go and try to look for the critical equation, right? Like in the 2D case, so we miss that if k is an integer, right? So what I tried to do with Joan Pedro was to look for the critical equation, right? And we were lucky and found that this is a nice equation that makes sense, right? So we went to the scale, instead to use k in integer, we just relax and say k is a real positive number, and then we got this. All right, so but then we obtain a nice local theory that is far from being optimal for S between 3/4 and 1. So we got a problem in 1, right? So we know we have existing solution in that space, but the continuous dependency is not working. Okay, so there are many problems, open problems for solution of this initial value problem. All right, so you can have a nice local theory in H1, right? So you will have a nice global theory, and then you will have a restriction of the initial data as in the previous example, and then you may try to see whether or not this equation has a blow up or not. Okay, so there's plenty of things to do in that case. Okay, so this is the advertisement, and now we keep going. And then again, I'm going to talk about the maximal function, and I want to motivate why talking about the maximal function, right? And so let's look at I'm going to follow Kenny Ponce Vega recipe to try to prove existing solutions for the initial value problem. And then what they do is consider the integral equation, right? Let's say this is the Zakharov equation. U, capital U here, is the unitary group that I'm gonna define in a few minutes. And then you try to estimate the L2 norm, right? Because you are interested in HS, and then you say, well, I wanna do L2 and the derivative in S. Okay, so what happens? So you can use, you just take L2 derivative, right? L2 norm, okay? So you use the property here. So you just put the L2 norm inside. Then you use this solution, the linear solution, that are unitary operators, right? So in L2, so you get that. And then in this point, you see that you are in trouble, right? Because you have a derivative, you want to control L2, right? If you put L2 here, you have to have an infinity of this guy. But on the other hand, there are some properties that say smoothing effect, right? And we know that the smoothing effect allows us to gain one derivative. So we are, there is no more choice but try to put this guy in the smoothing effect norm. So you do that. How do you do that? So you do Cauchy-Schwarz in time, and then you use Fubini, and then you have this, right? And then when you do that, okay, so here appears the smoothing effect, so you are okay. But then appears one norm here, and this norm is the maximal function estimate, or the maximal is a maximal function norm, right? So you have L infinity in these two variables, and LP in the X bar, right? So if you have a nice control of this guy, then you will have a nice result for the initial value problem, right? And so this is nice because you already have a time in front, and then there are chances to have a contraction mapping principle, and then use the contraction mapping principle, and then close the circle, right? And so here appears the maximal function naturally, right? And then if you have any k here, right? So you will have something in 2k, right? And then you are interested in to know if these things are good or not, if you have good estimates or not. Okay, so and this is what I want to try to convince you that you can do, right? You can sometimes use that, sometimes it's not enough, right? And then again, so we go and using the recipe of Koenig-Ponce-Weger, you study the solution of the linear problem, right? So we have to understand what happened with this. Okay, so this is the U that was in the previous slide. And then we want to obtain good estimates for the maximal function for this, not for this. Okay, so there are, in the previous result I mentioned, this is plenty of that. Okay, so we can see, for instance, in dimension 2, there is this result by Ademir Pastor and myself, and we got this estimate. So we got the L4 in X, L infinity, this is a maximal function estimate associated to this guy. And this is for S greater than 3/4, right? And then there is an extension for any time by Grunrock, okay? And so you have a better than this one, it's not only T01. And there is also an estimate obtained by Faminsky in the L2 norm, right? And with the same regularity. Okay, so this is one thing what we were trying to study, the modified CK equation. We have some doubts about the sharpness of this result or not, right? But it was okay for the purpose that we have at the time. Okay, so if you go to dimension 3, so you got this result by Axel von Rock. And then you will see here that you have only, this is the usual maximal function estimate, right? So you have L infinity in time, and then you have LP in the special variable, right? And so this is true for S greater than 3/4. And then if you use Sobolev embedding, you can obtain some estimate like this for S greater than 5/4. Okay? And then finally complementing these results, there is this one by Ribot and Bento, but then you have to add a time weighted maximal estimate here. Okay, so you have some time here, and then you got this nice estimate for s greater than 1. All right. And then if from those examples before, so you have 2 questions. So you have this the space-time maximal estimate. So that means you have the maximal estimate that we need when we are doing this contraction mapping principle, right? Okay, so how can given P in this range, how large can S be in order to get this estimate, right? And then you have the time only maximal estimate, the usual one, the same question, right? So what is the best possible value that we can prove, where we can prove this estimate, right? Okay, so we got this first result. This is a proposition saying that the first estimate satisfies if you are if P is between in this interval here and S is this number. All right. In the other case, if we have P in this interval and S the maximum of these 2 values. Okay, so that answer this this question here. Okay. All right. So, and then we have as a consequence of the following result. So we have the unitary group associated to the problem, right? So you have D equal to 3. So the best possible estimate is 1 here, according to this proposition. And this estimate is sharp, right? Up to this point, 3½ minus 1 over P. If D is equal to 2, then you get this estimate here. And again, we are good, right? So it's sharp to the endpoint. In the case P equal to 4 greater or equal than 4, or the other endpoint that is behind this thing that I never know how to get out of that. Okay, so S equal to 3, 4 in the case P equal to 2. All right, so what we do? Well, to prove this result, we use what has been done, right? So there are many estimates for the group, right? And the most interesting part is when you have D equal 2 and P equal to 2. And then what the idea of Joao was to use what Kinoshita proved, right? And instead to give an example, use the local well-posedness in order to prove that you cannot be better than this number, right? So S has to be greater or equal than 1/4. Okay? So you started with saying that you are better than 3/4, right? And then when you take the Kinoshita result, right, you get a contradiction of what Kinoshita proved is that if you are below 1/4, the map data solution is no C3, okay? And then you cannot use contraction. All right, so, okay, so he said that this method provides us through Sobolev embedding and argument contradiction for S greater than this number. This is the first part of proposition 1. And then in the second part, we had to use some non-resolved by Olin and Rogers, okay, related to Schrödinger operators in order to prove the second part, the proposition and so on. Okay, so regarding the Strichartz estimate, that I also mentioned that we had to do something in general, right? So we started with this 3-dimensional and 2-dimensional result that I obtained together with Ademir Pastor and Jean-Claude Sot. And then we have a general way to work with that is given in this paper with Hitman and Riaño, Rogers and Wright. And then, and this is also contained with in the work of Chipa for the critical line 2 over Q plus 2 over R equal to 1. Okay, so everything is together there. And then this is the Strichartz estimate in all the dimensions, right? Greater or equal than 3. Okay, so this is just to put together everything that we already know. Okay, so the particular case, K equal to R equal to 4, this implies the adolescent estimate obtained by Herr and Kinoshita, which enables the author to prove subcritical local well-posedness for the Zakharov Kuznetsov equation in any dimension, right? Whenever D is greater or equal than 3, an application of embedding the T variable really implies these estimates whenever S is greater than D over 4. And then we observe that this estimate is in fact sharp according to proposition 1. And so is the other space maximal estimate, which follows directly from the one above via Sobolev embedding. Okay, in the Y bar. Okay, so you got everything that we announced before in these cases that we are mentioning here. And then the final contribution for the employing the maximal estimates is this local well-posedness result, right? And then this is somehow complements what has been done by Sebastian Herr and Kinoshita and Grunbrock. So we have D greater or equal than 3 and K greater or equal than 4. And then there exist function spaces such that for any initial data in HS with S this number, the initial value problem 13 here is in this space, is a continuous function here. And then the map data solution is locally, right? Okay, so this is one of the main results. And again, we have, besides to use the local smoothing effect, then what we do is, yes, it's, as Joan Pedro said, it's heavily inspired by the works of Ribot and Bento and Grunbrock. And then we just miss the subcritical range K equal to 3 because of the lack of an estimate in this case, okay, in this space. All right, so let me see. Okay, so the last thing here is almost everywhere convergence, okay? And so I had to tell you what is the motivation of the whole thing, right? And then if you remember the class of the basic Fourier analysis, right? So we're starting with the maximal function associated to the Hilbert transform. And then one point is, well, you have this very nice operator, and then when this operator is actually makes sense almost everywhere, right? And then you have to go and study the maximal function estimate and everything. Okay, so this is again the maximal function is behind the story. Okay, so the motivation of that is this question proposed by Carlenson, and in the context of the Schrödinger operator. And so the question was, for which S real does it hold if you started with an initial data in HS, right? That this is pointwise. Okay, so you got this limit pointwise. almost every x. All right. So he showed that this is true if you take the initial data in h1 1/4 in n equal to 1. Okay, so this is the free operator, right? And since then, the study of this problem has been linear and nonlinear has gained a lot of attention. And then in particular, let me see if I'm missing something here. No. And in particular, there has been a lot of results. And then one complaint of the referee was to say specifically what result we were considering here, okay? And so we have several results of the theorem that we obtained here. The result by Grunrock in dimension 2, 3, k greater equal to 3, the Grunrock d equal 3, k equal to 2, Kinoshita d equal 2, k equal to 2, Molinet and Pilot d equal 2, k equal to 1, Herr-Kinoshita d greater equal than 3, k equal to 1. Okay, and then we obtain this result here. Okay, so we have that the solution converges pointwise, right, for almost every x in that D, if we consider the solution that I previously mentioned. Okay, and the technique that we employ here are inspired in the works of Erdogan and Strichartz for the KDB equation and Schrödinger case. And then some strategies introduced recently by Compaan, Lucà and Staffilani, sorry, which were responsible for establishing such results for nonlinear Schrödinger equation in higher dimension in sharp range, okay, using sharp pointwise convergence theorem for the Schrödinger flow. All right. So these are the results. And then, well, I have the idea for the proof. Let me see how many times I have here. And then I was telling Claudio that this is really technical. And probably I'm going a little bit fast, just telling you more or less how are the things, right? So in the case of the proposition 1, we have an explicit initial data, right, constructed in the usual way, like so you have a product of these two functions supported in some places here on the line, right? And then we can show the psi of the norm. Okay, so if this guy allow me to show you. Okay, there. So we can compute the HS norm of this guy. And then we can plug this initial data in the inequalities, right, that we are trying to perform. And then we found, okay, so we will have to prove this. In one side, we have this lower bound, and we have this upper bound. And then in order to get this inequality, you have to ask what we have in proposition 1, all right? To prove the second one, so we do something like this. So we suppose that this is true for some p greater than 1, right? So we have L infinity only in time, and then LP in the spatial variables, right? And suppose you have this inequality, right? So you want to prove that you cannot do better, right? And then you have, if you want to do like LP in X, right? Ly, LT in infinity, right? So you need to pass by using Sobolev, right? And then you get this. S has to be like this. But then if S is greater than this, it's because R has to be like that, okay? And this, so we have the max, is either this number or this number, right? But this number, you have to look, well, this restriction here, you have to work a little bit more. And then we need to use, for instance, this result of Jolene, right? And then we get exactly this for this value of S, but this is only in this ball, right? So we have to extend this stuff in the whole space. And this can be done using this result by Keith Roger, right? So you can have all this estimate in the whole space. Okay, combining these two things, we can obtain that S has to be like this, and this is what we claim in the proof. All right. All right. So for the theorem 1.1 probably. So we have this. I will just tell you a little bit about this in the case d equal to 2, because it's the nice one. I'm talking about this. We have this estimate, right? So this is true for s greater than 3/4. And then we want to show that this is exactly that. All right. And then, so we don't construct a counterexample, as I mentioned before, but use the local theory of Kinoshita, right? So we have this estimate already. And then you try to prove a local well-posedness for this guy, right? And you can say, well, you can do better than this, right? So S greater than S not less than 3/4, okay? Okay, using the maximal function estimates, and then get a contradiction with the result of Kinoshita saying that you don't have the application data solution is now C3 if you are below 1/4. Right? Okay, so in this case, we have to define what is the space, right? This is the space that we are working with. So you got the usual solid space, and then you got the smoothing effect, and then the maximal function estimate. All right. And then you claim that, well, in the linear part, no problem. All the estimates are planned to satisfy this condition. And then we get this, right? So we use the Duhamel, the integral version of the divisor value problem in this way. And then using the method of Ribot and Bento, that is basically use a paraproduct here, right? So we can estimate this part in this way. Okay, so I jump in a lot of technical stuff. And then you keep estimating this part, right? And then you get the time that you need in order to close the contraction. And in one point you say, well, okay, so we run this argument whenever S is greater than this number, right? And then by the Picard iteration method, we will obtain local well-posedness in HS, right? S greater than this number. And then you actually have that if S is greater than this number, S0 minus 1 minus 1/2, there is delta that satisfies this condition, right? This is one side. And then the nonlinearity 16, in 16, this one here, right? The nonlinearity is smooth, right? And then if we are using contraction mapping principle, we can prove that this is actually it's infinity, right? Okay, somebody said something. Okay, so in particular, you can say that you the application data solution is an infinity, right? And then in particular for S graded smaller than 3/4, you will have that. But that's not true because it's otherwise Kinoshita resolved with the faults, right? And so this is the very fast and without any detail, how this works, right? Okay, so everything that I say here is regarding local well-posedness, right? But then there are different directions in research for this CK model. And then I can mention the asymptotic behavioral solution, for instance, the result of Argenis Mendez with Claudio, Poblete and Pozo, Felipe, one of them. And then regularity of solutions, saying the propagation of regularity by Argenis Mendez. Stability of solitons, Rafael Cot, Claudio Muñoz, Didier Pilot, and Simpson, and then Frederic Valette for multiple solitons, right? And then also the unique continuation principles, you can find this, resolved by Cossetti, Fanelli, with myself, Bustamante, Jimenez, and here. Okay, so I say obrigado pela sua atenção. Thank you for your attention. Muchas gracias por la atención.
Many thanks, Felipe. Thank you so much for your talk. I don't know if there are questions in the audience or for the participants that are online. If you have questions, just please go ahead and ask your question, please.
Yes. Mike.
Mike, go ahead.
Hi, Mike.
Let me ask a stupid question, because you considered only K 1, 2, or 3 basically, right? So there is no other K in the nonlinearity.
No, yes, I consider all the Ks.
Okay, and is there a difference between all these powers, or is it the same, more or less? Is some effect, you know, with the higher nonlinearity, then it is easier to show the result, or no, or the nonlinearity is not important in some sense?
Yeah, basically, if K is sufficiently large, yes, there is no big deal to control them, right?
Okay.
Then the problem is when you go down, right? So K1, 1, 2, 3 are complicated.
Okay, and is there a difference between K, this relation between K and the dimension? Let's say, you see, so everything works with, for instance, in dimension 2, you can allow any K, right?
For dimension 2, yes, you are allowed. Yes, you don't get sharp results sometimes, right? For instance, in the K equal 1 and 2, right? So you are above the scale.
Okay.
Right?
Okay. Okay. Well, thank you very much. And just one last question: when are you going to come out from the hotel? When did you arrive?
I really would like to know.
So, but when did you arrive?
On Tuesday.
Oh, so it's a long time. Okay, well, I hope everything will work out soon, and we will get together in person.
Okay.
Okay.
Thank you.
Thank you, and welcome to Chile.
More questions?
Hi, thanks, Professor Felipe, for the talk. What kind of unique continuations do you have for these equations?
For the equation? Yeah.
You mentioned some unique continuation results.
So we got the okay, so for instance, you have some decay, right? And then you can see that you can now be above this decay. And then, for instance, you have two different times. Okay, and you have the solutions with some decay, right? Exponential decay. And then they have this exactly the same decay in different times. Then in the middle, right, they have to be identically equal to 0.
Okay.
Okay. This is the kind of unique continuation, what is called the asymptotic unique continuation.
Okay.
All right.
Okay.
It's not the other one we're using Karleman. Well, we use Karleman, but in that spirit, right?
Right.
I have a quick, easy question. You already mentioned this when you were motivating. When k equals 2, you used a Duhamel formula and you passed over quickly over a smoothing effect. Can you show the spaces again in that, or that slide again? Because
okay. So I said, when I was doing the example here, here. In that one?
Oh, there is a D. Okay. There's delta X in the last line.
Okay, so you got the smoothing effect in this side, right? And then you have to pay with the maximal function estimate in the other component, right? And this is usually the one that gives some constraint, right? In order to get the local result.
Okay, thank you.
Okay.
More questions? No? I just have a sort of, I don't know, I mean, I don't know how to qualify this question. So your maximal function involves the y variable and the time variable, but there is no clue about the geometry behind the, I mean, in the definition of the maximal function, maybe inside of the proofs, but it's in the definition of the maximal function, there is no geometry. There is not this famous cone of CK. So my question is maybe, do you think that your technique also applies to other models with different nonlinearities? I think of KP for powers different than 2. And do you think that is independent of the geometry?
No, I don't think so. Yeah, the actual maximal estimate for the KP equation are quite complicated. Okay, so you have some regions, they are very nice. Okay, but in other regions are really bad. Okay, so there is no an estimate, like you say, a complete estimate in all the directions. Okay. So you have one part is behave like that, and in other part of in other region behave differently. And then that's one of the points when you try to do this argument for the KP. So you run out of a maximal function estimate that just says something about the regularity.
Okay, perfect. I see. Thank you.
No problem.
No more questions? No? So if not, let's thank Felipe again. Thank you, Felipe, for your talk.
Thank you.
We are sorry, I mean.
No problem.
Okay.